Now we look at one common measure of strength for linear relationships between two quantitative variables. Pearson's correlation coefficient, denoted with the lowercase r, is a numerical measure of both the strength and direction of a linear relationship between two quantitative variables. In general, the term correlation coefficient will imply Pearson's correlation coefficient. You would need to specify or be told if it is some other correlation coefficient. And there are other correlation measures. The formula is provided for those who are interested, but we will not be calculating this value by hand. It's very important to note that this value is only interpretable for linear relationship, as it specifically measures the linear association between two quantitative variables, not any other type of association. Again, you can only rely on this measure for linear relationships. So either you are told that it's linear, or you see that it is reasonably linear by looking at the scatter plot. For any data set, the correlation will always be between -1 and 1. If there's no relationship between two quantitative variables, there is absolutely a flat line through the data, and the value of Pearson's correlation will be 0. If there's a perfect positive, increasing linear relationship between the two variables, the value of the correlation will be 1. And if there's a perfect negative, decreasing linear relationship between the two variables, the value of the correlation will be -1. In the cases of a correlation of exactly 1 or -1, every point would fall exactly on the line. Thus, the closer the correlation is to 0, the weaker the linear relationship, and the closer to 1 or -1, the stronger. The sign tells us whether the relationship is positive, increasing, or negative, decreasing. Be aware that, although we do desire values of the correlation which are close to 1 or -1, indicating a strong relationship, in reality, when we study two variables, it is not necessarily bad or even surprising when the value of the correlation coefficient indicates a weak linear relationship. For example, if we look at heights and weights of people, if we take 10 people of the same height, we expect them to have a wide range of weights. If we're interested in summarizing the relationship, this is simply a fact of the data. We cannot make the relationship stronger, but clearly height and weight are related and tend to increase together in a systematic way. Some facts about the correlation. It doesn't matter what units are used for the two variables. If I have height and weight in inches and pounds, and then I convert them to centimeters and kilograms, when I graph both sets of data, the scatter plot will look exactly the same. And so we would want a measure of correlation which gives the same answer. And it is true that Pearson's correlation coefficient would be exactly the same for both sets of data. That will not be the same when we get to linear regression and the slope. Once we start saying, as x increases, we will be specific to the units of the current x variable, and we will get a different slope if we change the units of our problem. The correlation has no unit of measurement. It is extremely important. I can't stress this enough. Do not use Pearson's correlation coefficient if the relationship is not linear. It only measures the strength and direction of a linear relationship between two quantitative variables. It ignores any other type of relationship, no matter how strong it is. I can have a perfect relationship where the correlation is 0, and if I say there is no relationship based upon the correlation, that would be completely incorrect. One question we want to address is how do different kinds of outliers affect correlation? We're going to use the applet linked on this slide to illustrate, although we aren't using it for its original purpose. You can add and delete points. To begin, I created a basic scatter plot. Then I added an outlier that is not in line with the pattern. When we have an outlier that is out to the side in some way, like the one in the scatter plot on the right, the correlation moves closer to 0, indicating the weaker trend due to this type of unusual observation. I then added an outlier that is in line with the pattern. When we have an outlier that is in line with the pattern of the data, but simply far away from the rest of the data, this strengthens the relationship. We find that the correlation is closer to 1 or -1, depending on whether the relationship is increasing or decreasing. Let's take a look at a more extreme example. On the left, we have a new scatter plot of a random cloud where there's basically no relationship. The correlation is very close to 0. Then I added a point in the far upper right corner. Now the correlation is around 0.57. This is a huge difference, and all due to the one single outlier. In this case, the correlation of 0.57 is entirely fabricated by the outlier and would be a misrepresentation of the data. You can see from these illustrations that outliers can have a dramatic impact on the value of the correlation coefficient, and thus we need to take them into consideration when we interpret our results. It might be useful to calculate the correlation with and without the outlier to understand the effect of the outlier in a specific scenario. Here are a few examples of scatter plots along with the value of the correlation coefficient. First, we have the driver age versus sign legibility distance. This is a reasonably linear trend, and thus it makes sense for us to talk about the correlation. In this case, we have a relatively or somewhat strong decreasing relationship with a correlation of negative 0.793. Then we have another reasonably linear trend for the relationship between introductory course average and upper level course average. The correlation is 0.931, and clearly we have a strong linear increasing trend in the scatter plot. The next two are not linear, and thus the correlation should not be applied, but we wanted to show you what happens in these cases. Both of these scatter plots show a strong, nonlinear or curvilinear relationship between the x and y variables. In the speed versus fuel used, the correlation is negative 0.172. If the relationship were linear, this would say that we have a very weak decreasing linear trend. If we were to fit a line to the data, it would not fit well, and the closeness of our points to that imaginary line is what the correlation measures. If we were to use the correlation and interpret this value, we would be misrepresenting the data, as there is actually a very strong relationship between x and y. In fact, almost perfect if we fit the correct model. For the incentive versus percentage returned, we have a strong nonlinear relationship. Here the overall trend is positive, and we get a correlation measure which indicates a strong positive relationship. However, if we had a line with the values as tight as we see here, the correlation would be much closer to 1 than we have for this nonlinear trend. Again, care must be taken to avoid misrepresenting the data when interpreting the correlation coefficient. If the relationship is linear, then it will tell us if the relationship is positive or negative and provide a direct measure of how strong the relationship is. It is difficult to give clear guidelines for what constitutes strong or weak, but it is easy to discuss stronger and weaker when we have a few scatter plots to compare. Here is our example from the applet on x equals social distress and y equals brain activity. There is a reasonably strong linear positive trend seen in the scatter plot. On average, larger values of social distress are associated with more brain activity. The correlation is 0.8782, confirming what we see. Look through some of the other data sets in the applet and see how close you can get to guessing the correlation. To summarize, Pearson's correlation coefficient is a common measure of the linear association between two quantitative variables. It measures both the direction by the sign of the value of the correlation and the strength by the magnitude of the value of the correlation. It measures both the direction by the sign of the value of the correlation and the strength by the magnitude of the value of the correlation. The closer to 1 or negative 1, the stronger. The closer to 0, the weaker. We need to be careful about outliers as they can dramatically impact the value of the correlation, and we must verify linearity by looking at the scatter plot.